Welcome to the lab. Today, our goal is to determine the saponification number of a groundnut oil sample. Let's look at the principle in our lab manual. The saponification number is defined precisely as the amount of potassium hydroxide, or KOH, measured in milligrams, required to completely saponify exactly 1 gram of fat or oil. To understand what that means, we look at the chemical mechanism. When we heat lipids in an alkaline medium, the reaction splits the large triglyceride molecules. They break down into 3 smaller soap molecules and 1 glycerol molecule. This reaction gives us a useful scale. Because smaller molecules require more KOH to react per gram of sample, a higher saponification value indicates the presence of shorter fatty acid chains. Conversely, a lower value points to longer chains. By running this test on our groundnut oil, we can verify its exact chain length profile. That data will tell us definitively if this specific batch is structurally sound for commercial soap making. Let's set up the experiment. Returning to the manual, our apparatus and materials list requires the fat sample itself, alcoholic potassium hydroxide, standard hydrochloric acid, and phenolphthalein indicator. Before pouring anything, ensure all glassware is completely clean and dry. Any lingering water contamination will dilute the alcoholic KOH solution and compromise the entire reaction. Step 1 is sample preparation. We start by carefully transferring exactly 2 grams or 2 milliliters of our groundnut oil sample into a clean 250 milliliter conical flask. Next, we add exactly 25 milliliters of 0.5 normal alcoholic KOH directly to the flask containing the oil. Potassium hydroxide is highly reactive, and its dilution is exothermic, meaning it releases heat. Standard safety gear, including gloves and goggles, is mandatory to protect your eyes and skin from direct contact. The flask now holds a volatile, unreacted mixture. To drive the chemical breakdown, we need to introduce heat, but we must control that process perfectly to avoid losing our solution. According to the refluxing procedure in our notes, the next step is to attach a reflux condenser to the neck of the flask before moving it to the water bath. The condenser acts as a trap. Cold water circulates through the jacket, cooling rising solvent vapors. They condense into liquid and drop back into the flask, preventing evaporation. We then maintain a gentle boil for 30 to 60 minutes. Throughout this heating period, you need to lift and swirl the flask occasionally to ensure the lipids mix thoroughly with the alkaline solution. At the end of that hour, the groundnut oil has been entirely saponified. What remains in the flask is the newly formed soap, plus an unknown quantity of leftover unreacted KOH that we now need to measure. Remove the flask from the heat and allow it to cool. Then, add 2 to 3 drops of phenolphthalein indicator. Because the solution is highly alkaline from the leftover KOH, the liquid will turn a dark pink. Here, in the titration instructions, our goal is to neutralize only that excess KOH. We do this by titrating admixture with a standardized 0.5 normal hydrochloric acid solution. Add acid from the burette drop by drop, swirling continuously. You are looking for the exact endpoint where the solution flashes from pink to clear. Once it turns colorless, read the burette and record the exact volume of acid used. We label this value VS for volume of sample. To make sense of that number, our journal notes specify we must run a blank experiment to act as a control baseline. For the blank, we repeat the process. We measure the alcoholic KOH, attach the condenser, and boil it, and titrate it. The only difference is that we completely omit the groundnut oil sample. Titrate this control flask to make a cumulus endpoint and record the total volume of acid used. This is your VB, or volume of blank. When you compare the two, your VB will always be higher than your VS. Without any oil present to consume the potassium hydroxide during the heating phase, the blank flask retains much more KOH, requiring significantly more acid to neutralize it. With our 2 volumes recorded, we turn to the calculation page to find our final saponification number. Inside the formula, we have 2 constants, the normality of our acid solution, which is 0.5, and the standardized molecular weight of potassium hydroxide, which is 56.1. Now we plug in our experimental data. Our blank required 32.6 milliliters to neutralize, and our sample required 29.2. We subtract the sample volume from the blank volume and multiply by our constants. Completing the arithmetic gives us the exact saponification number for our batch, 190.74. The final step is validation. Looking at previous studies, the standard literature range for groundnut oil sits between 190 and 210 milligrams per gram. Our result of 190.74 lands safely inside that window. This confirms our laboratory execution was accurate, verifies the presence of the expected short-chain fatty acids, and proves this oil meets the chemical requirements for commercial soap production.